So we all know that working with electricity is dangerous, right? I mean, that's what makes it cool. It's all about the rush! Okay, well, maybe not. But electricity is pretty cool, and that's why you're here, because you want to learn how to play with it. Maybe you want to build yourself an American Ninja Warrior course in your backyard for squirrels, but you don't want to electrocute yourself, and you don't want to electrocute any squirrels. Or maybe you do. Just don't, guys. That's not why we're here. So why are we here on this very first video on Life Meet Lightning? We're here to talk about electrical safety so that you don't turn you into a barbecue squirrel. So later on, we're going to talk a little bit about the hazards of working with electricity, and I'm going to give you 19 tips that you can use to avoid shocking yourself or otherwise injuring yourself working with electricity. And then I'm going to give you some of my own oops moments, and you can laugh at me and make fun of me, but it's to make you aware and extra precautious when you're working with electricity, and maybe you can leave your own oops moments in the comments so everybody else can make fun of you too. So if you find this video informative or entertaining, please like, subscribe, and stick around because we're going to get into it. So what exactly makes electricity dangerous? Well, the primary hazards of electricity are shocks and burns, and the secondary hazards of electricity are fires and falls. But before we get too far into that, let's start off with some fun facts. Dictionary.com defines electric shock as a sudden discharge of electricity through a part of the body. Guys, you aren't meant to conduct electricity. It's just not good for you. Unless you've had a heart attack and you're in the hospital getting defibbed. But on that note, the difference between electric shock and electrocution is death. Moving on. Now you can win that $1 million question on Who Wants to Be a Millionaire? Okay guys, so to talk about the hazards of working with electricity, first we need to talk about a few things. Voltage, current, and resistance. And don't worry, we're going to talk a lot more in depth about this stuff later on in the series, so make sure you subscribe and stick around. But for now, go ahead and picture a river, or better yet, let me show you a river. When we think about voltage, imagine you are out there standing in the river. Voltage would be the pressure of the water against you. It's the force of the water flowing downstream. Current, on the other hand, would be the water itself rushing past you, the ice-cold water trying to steal your very soul. Resistance would be you standing in the river, just getting in the way. How rude. Oh, and all those rocks out there causing all the turbulence. That's resistance. Resistance is the obstruction to current flow. So what causes electric shock? Well, a popular misconception is that voltage is what causes electric shock. But in reality, you could go out and touch a 10,000 volt power line, and as long as there's no current running through you, you'd be just fine. It's actually current that causes electric shock. Now, with that said, current is a direct result of how much voltage there is present to drive it and how much resistance there is present to hold it back. Now, as an analogy, instead of a river, imagine you go out and stand in a lake instead. There's no force against you like there was with the river because there's no pressure trying to drive that water anywhere. So now that we have a basic understanding of voltage, current, and pressure using some water analogies, let's talk a bit about the damage and lethality of current flow through the body. So the damage that current can do in your body really depends on two things. It depends on A, the path that current takes through your body, and B, the amount of current flow that exists in your body. And for current flow to exist, and this is really important, take notes, this is something to remember from here for your whole electronics journey. For current flow to exist, it has to have a path from point A to point B. So in order to get shocked, like I said before, you can touch a 10,000 volt power line and be perfectly fine as long as there's no current flow. In order to get shocked, you have to have a path from point A, being your hand, and point B, your other hand, or your foot, or your head, or whatever. Current has to have a path to exist. So to get shocked, you have to create a path for current to flow. And that's a fundamental concept. Remember that. And a second fundamental concept about current is that current always takes the path of least resistance. So if you think about the water analogy, again, the river on the mountainside, the water flowing down the mountain's always going to take the path of least resistance. That's common sense. You know, water, when it flows downhill, is going to take the quickest, easiest path. The path of least resistance. So how much resistance does your body offer? Well, since electricity existed, there have been plenty of scientists that have studied its effects on the human body, and there's lots of information out there. If you want to go down the rabbit hole looking into that stuff, you certainly can, but The general consensus is there's about 100,000 ohms of resistance in your body to electricity. And you may not know what an ohm is yet, but on a scale from 0 to a lot of resistance, that's a pretty decent amount of resistance. And another important thing to note too is that from your left hand to your right hand, you have a longer path than from your thumb to your index finger. So the distance of the path that it has to travel through makes a difference too. So if you're gonna get shocked from your left hand to your right hand, it's takes a little bit more voltage to push the current across that path than it does from your index finger to your thumb. Now, the goal of this channel is to provide a simple but in-depth explanation of electricity. And we're not going to go down the rabbit hole at this point, especially this first video, you're new. I'm trying to give you a foundational platform of knowledge. If you want to go down the rabbit hole with something like this later, you'll have that foundational knowledge that you can. My own research, like making this video, I wrote down everything that I remember, everything that I wanted to bring up. Then I went through a lot of my textbooks, old textbooks. I went on, did a little internet research. I looked through my old school notes and kind of came up with a conglomeration of information. And especially like a little later on, I'm going to talk about how much current can kill you, or the effects of the amount of current through your body. And with that stuff specifically, like there's one study may say one thing, another study may say another thing, but I came up with a conglomeration of information based on a bunch of research that I did. So it's, the human body is a special thing. Somebody's resistance might not be the same as another person's resistance, and that kind of affects those studies and stuff. But just keep that in mind. Again, trying to provide a simple but thorough foundation of knowledge with electricity. So with that, we'll move on. Alright guys, I know we haven't talked about scientific or engineering notation yet, or metric prefixes. We're going to get to that in the next video, so if I haven't said it enough, please subscribe, like, comment, help me out. There's a lot of great content coming up. I'd really appreciate it. In the meantime, when I'm spitting out these current numbers, I'm going to give you some real world examples here just so you can kind of relate to what I'm talking about. So the very lower end threshold of current that could potentially kill you is about 2 to 4 milliamps. And that's if it takes a very specific spot, a specific path in your body. Right across the heart's a good candidate right there. But that's the very low end of the amount of current that could potentially kill you. And just to help you kind of relate, your typical LED indicator lights, you've seen them all over the place, like little red lights on your computer, green lights, they're pretty popular, LED lights. This little blue light back here behind me, that's an LED light. Those typically draw about 10 to 20 milliamps of current. So that's quite a bit more than the lower end of the amount of current that could potentially kill you. And in that same range, about the 15 to 25 milliamp range is what we call the let go threshold. You may have heard of the grip of death before. Electricians may have heard of that, but that's what we're talking about. The let go threshold is when you get enough current being driven through your body that it overrides the signals in your nerves that control your muscles. So you may have heard stories about somebody grabbing onto a power line or something and they start getting electrocuted and they can't let go because that current that's flowing through their body seizes their muscles up and they can't let go. That's what we call the grip of death. And again, remember guys, the point of this video is to help you recognize the hazards and what could potentially happen so that we can take the proper steps to avoid, serious stuff like that happening, and so that we can avoid becoming barbecue squirrels. Moving on. At about 70 to 80 milliamps is the ventricular fibrillation threshold. Ventricular fibrillation, sorry guys, hard word to say, but ventricular fibrillation is when your heart just up and cuts down and doesn't want to work anymore. It just sits there and quivers and doesn't pump blood anymore. Now, at about the 240 to 250 milliamp range, that's when that ventricular fibrillation gets into the lethal zone. More than a few milliseconds, a few seconds of exposure could kill you. Now, just for perspective, your little charger cord that you might charge your phone with, one of these guys, this cord is probably sending anywhere from 500 to an amp to maybe 2 amps through it at any given time. So the numbers we're talking about, 240 to 250 milliamps, is less than your charger cord on your phone is running through it to charge your phone. And so it's still very, very low numbers. So let's go ahead and jump to the next tier or whatever as we're going along. Jumping up a bit more, around the 4 amp range is enough current to just stop your heart entirely. It didn't even have time to get out the door and go on vacation. It just dropped dead. That's about the point where your heart just induces paralysis and pretty much guaranteed death at that point if that kind of current gets across your heart. And 5 amps is the barbecue zone, where it actually starts cooking your flesh. Fun stuff. Don't do that. I don't recommend it. Now, none of this, like I said before, is meant to scare you off. It's simply to make you aware of the hazards that you might face working with electricity. You know, driving's dangerous. Existing on the planet Earth is dangerous. An asteroid could come through my roof and kill me right here and now. Existing's dangerous, but you know, we're smart creatures, and we take precautions based on the knowledge that we have. And that's what this is all about, you know, learning about this stuff so that we can take the proper precautions. So let's go ahead and talk about the precautions that we can take now. I'm going to go ahead and give you a list of 19 tips that you can take to the bank to help you avoid becoming a barbecue squirrel. I feel like I'm starting to say that too much, but it's okay. Alright, so I've tried to make this list as inclusive as possible, whether you're working on low power circuits on a breadboard or whether you're installing a 250 horsepower motor on something. I'm definitely going to refer back to this list as I'm going along, probably give extra tips here and there, but I've tried to make it as inclusive as possible, and I definitely recommend taking notes and referring back to this as you're going along and as your understanding of electricity increases. So, without further ado, let's get into it. Alright, tip number 1, work with the power off unless testing or measuring. There should be almost no circumstances where you have to work on something that's powered on. Come on guys, usually just laziness if you're going to work on something with the power on. Turn it off. Just be extra cautious. We just talked about all the bad things that can happen, the accidents that can happen if you're working on something with the power on when you don't need to be. So that's tip number 1. Alright, tip number 2, use the one-hand method when taking measurements and or invest in a pair of insulated gloves. A lot of old timers, you know, they never used to use insulated gloves. You'd see them digging around, measuring in high voltage cabinets with just one hand. And the logic behind this is, like we talked about earlier, you can't get shocked if there's no current, and current needs a path, right? So if you're eliminating the paths a current can take, then you're not going to get shocked. Now, granted, when you're using the one-hand method, typically you have insulated boots on, or you're standing on something on the floor that's insulated. But that's kind of the logic behind it. You know, getting in the habit, even if you are wearing gloves, to measure high voltage stuff with one hand. It just eliminates the paths, and especially the most dangerous path, like we talked about, right across the middle of your body. It helps eliminate paths for current to flow. So tip 2, use the one-hand method. Alright, tip number 3, guys, discharge capacitors. I know you probably don't know what a capacitor is yet. We'll talk about those later. But for now, I'll go ahead and put up a picture so you can kind of recognize what a few capacitors might look like. But a capacitor is basically an electronic device that stores a charge, kind of like a battery. You can find them in almost any circuits, any electronic devices anymore. Sometimes the voltage levels on these capacitors are stored at a very high charge. For instance, your microwave in your house or the old-fashioned tube TVs can store up to 5 kilovolts to 35 kilovolts. Those are very high levels of voltage in those capacitors. And again, we're talking voltage because remember, current is what causes electric shock, but you need to have the pressure to actually push the current through the path in order for you to get shocked. So capacitors, check them, discharge them before you start working on anything. Make sure you're checking and discharging capacitors. All right, tip number 4, be aware of your position and your surroundings. Remember, this one of the secondary hazards of electricity were falls, and most of the injuries that actually occur from electricities happen as a secondary component. You know, you're working on a ladder, rewiring something in your roof, and you didn't realize the power was still on. You zapped yourself, you fell off the ladder, broke your hip, broke your neck. Not good, guys. So be aware of your position and your surroundings, and also be aware of your tools. You know, sometimes accidents happen because your tools accidentally fell off of something and made contact where they shouldn't have made contact, and you got nipped in the butt by it. So be aware of your position and your surroundings, and we'll get to the next tip. All right, tip number 5, guys. Be aware of your probe and wire insulation. Check it before you power it on. Insulation's that, fun rubber stuff around all your power cords that's there to keep you from getting shocked. Check it. Sometimes they get worn out. You might have frayed wires exposed, and it could shock you. So check that stuff before you take measurements or before you energize something or touch something that's energized that might be damaged. All right, tip number 6, keep your grounds intact. We'll talk about grounds a little more later on in this series, but for now, see that little third prong on your electrical outlet plugs, that little bottom one? That's your ground. If your device is supposed to have a ground and it doesn't, do not use it. Those grounds are there for your safety, they're for your protection. Remember, earlier we were talking about paths and how electricity wants to take the path of least resistance. Well, that ground on there, that's your path of least resistance. If something happens in your device, your vacuum cleaner, or whatever you're working with, and that ground isn't there and one of the hot wires in there gets loose and touches the case, well, normally that extra current would go through the ground wire, but if that ground wire is not there and you touch it, that's going to go through you. So make sure your grounds are intact. If it's there, make sure you use them. Don't use something that doesn't have a ground. Moving on. All right, tip number 7. Drinks, electricity, gotta keep them separated. No, seriously though, if you must have a drink at your workstation, use a lid, use a cap, use something that can be closed, because, we're humans. We make mistakes. Sometimes that mistake is dumping your water all over an energized circuit, and you could get shocked. So best case scenario, just don't have them. If you have to have them, use a lid. Use something that's not going to come off if you spill it. Tip number 8. Do not work with electricity when you're tired, medicated, or drunk. Just don't do it, guys. It might sound fun at the time. Just put a lock on your door or something. Don't do it. Tip number 9, guys. Have a plan for the worst. Remember, one of the hazards of working with electricity was fires. So if you're working with electricity, you should probably have a fire extinguisher around, and make sure it's rated for electrical fires since you're working with electricity. Also, if you're working with higher voltage, have a buddy and probably make sure he knows CPR. Good advice. Tip number 10, guys, know your equipment. Remember, we were talking about capacitors earlier and recognizing the hazards that are present on almost anything electronic. Well, know your equipment, know what you're working with, know what you're using to measure stuff with. It can be really dangerous to measure high current on a multimeter that's not rated for the current you're measuring. So know your equipment, know what you're working with. On to the next tip. Tip number 11, wear safety glasses, don't wear jewelry. Jewelry can inadvertently make contact with some high voltage circuits you may be measuring, and it could zap you, so just don't do it. And safety glasses are always a good idea if you like your eyes. If you want to go blind, you do you, man. But safety glasses, don't wear jewelry. Tip number 12, guys, use grommets and bushings when you're routing wire into pandles or through conduit. I'll put up some pictures so you kind of know what I'm talking about, and of course I'll address this later when we actually get to that topic down the road. But if you don't use grommets or bushings, over time, especially if you're routing wiring to a motor or something, that the sharp edges on those can rub into your insulation and eventually short out whatever wires are going across it. So make sure you're using bushings and grommets, and we'll get on to the next tip. Tip number 13, maintain a clean and organized workstation. I know sometimes when you're working on a big project, it's really hard to maintain order, but I highly encourage you to at least try. It'll help prevent accidents from happening. Grabbing something that you thought was something else that might have been live and might have shocked you. Again, don't work on stuff live, but maintain a clean and organized workstation, and that'll help your sanity too, which will also help prevent accidents from happening. Moving on. Tip number 14, always check your power ratings. This is kind of a nod to the whole know your equipment thing, but make sure you check that stuff. If you're planning to run 600 volts across a wire, make sure it's rated for 600 volts, or probably even more than 600 volts. Don't use a wire that's rated for 300 volts if you're planning to run 600 volts on it. Know your equipment, know what you're working with, know what it can handle. Tip number 15, use proper enclosures. There's all sorts of places you might want to build a panel for. Make an electrical box. If you're going to put it outside, make sure it can stand up to the elements. If you're going to put it somewhere hazardous, around gasoline or some place that might explode, make sure you got one that's rated for explosive environments. Also, if you're going to use a metal enclosure, make sure you ground it. If you're going to use a plastic enclosure, make sure the insulation rating can hold up to whatever you're putting in it. Tip number 16, hook up your power last when working on a project. It might be a little thing, but it's engineering safety into your workflow. If you're working on something, maybe you unhook something that you forgot about and you go to power it on. Well, you can't power it on if you don't have a cord to plug it in. So if you're working on something, do your power wires last. Engineer safety into your workflow. Tip number 17, consider using a GFCI outlet to power your projects. Now, we'll talk about this stuff a little bit later on. Fuses and circuit breakers are meant to protect your circuits. They're not meant to protect you. GFCI outlets are meant to protect you. So I'll put up a picture, so that you can kind of see what I'm talking about. I'm sure you know what they are, recognize them, but some things to note about GFCI outlets. First, they don't necessarily prevent shock. What they do is they monitor the amount of current that's coming into and going out of the outlet. So what that means is if you stick your fingers in there into the GFCI outlet on both sides, the current's going to go in your thumb, around through your finger, assuming none of it's escaping the ground. But a GFCI outlet won't necessarily keep you from getting shocked. If that's the case and it's going through your fingers, seeing the same amount of current, typically, it depends on where it's set, but it might not necessarily trip. It's called a ground fault circuit interrupter because it's looking for leakage current to ground, something that might flow through your finger down your foot into the ground and not return to the outlet. That's what they're looking for. So if that happens, it'll probably trip. I think the span is like 20 milliseconds. It's a very, very fast trip, and you're still going to get shocked, but it'll protect you from getting electrocuted. Some things to note about GFCIs, though, is some devices that you try to power with them don't necessarily work well with them. If you've ever noticed in your kitchen, if you tried to run a blender or if you ever tried to run a vacuum on a GFCI outlet, it probably tripped it. And that's because of the inductive loads that you're putting on it. We'll talk about that stuff later, but just something to be aware of for now. Depending on what you're trying to power, it might be a pain in the butt. And what I would recommend is getting an external GFCI outlet so that you can just plug it in when you need it, plug whatever you want into it. If you're working on something that doesn't like it, doesn't behave with it, you can just unplug it and use a regular wall plug. But it's always a good idea, any extra device in there that could help you keep you from getting electrocuted. It's a good one in my book. All right, tip number 18, use industrial lockout tagout procedure. This tip might seem kind of silly at first, especially if you're a home hobbyist, but if you're working on something that's high powered, if you're working on a light fixture or something and your girlfriend, your wife, or somebody comes home and notices, hey, part of the house isn't on. Let's go reset the circuit breaker. It must have tripped, and you're up there working on it. Not a good thing. So I'll talk a little bit about what that is. So in my field of work I work as an industrial maintenance technician, and we have a procedure we follow anytime we're going to work on a high voltage machine, well, any machine basically, but Uh, our first step is notifying our supervisor. In your case, it might be, if you got a wife or girlfriend, tell them you're going to be working on something so they don't go power it on. Just be aware of that and make sure they know about it. Second step would be to power down the machine, put on an arc flash jacket and insulated gloves, and tape off the area. Set up a barrier so nobody can come anywhere close to what you're working on. That's what we do at work. I'm just giving you can take it for what it is, but in an industrial setting, that's just what we do. We tape off the area. Second step, we put a padlock on it with a do not operate tag with our name on it, so we know who's working on something, who locked it out, and why. Uh, Next, we take our meter, we test our voltage meter on something that's working, make sure our meter's working. Then we come back and we test it on what we just shut off to make sure the voltage is actually disconnected. There have been times where at work we found stuff where we flipped the machine off and it didn't separate one of the phases and there's still live power going to it when we thought we had it switched off. So that's part of the reason we do this. We test it on something that works, make sure our equipment's working, test what we just powered off to make sure it's actually powered off. Then we retest our equipment again just for redundancy, make sure our meter's still working properly. And at that point, we can take off our gloves and stuff and actually work and do the work that we're there to do. So, how to apply this to your home. So, if you're like doing some wiring in your attic or something like I've been talking about, you can get these little devices. I'll try to put a picture up. Maybe I'll put a link in the description or something. But you can get a little a little device that's meant to lock out your circuit breaker. You just screw it on there. You put a cover over it, put a padlock on it, and that way, if your wife, girlfriend, somebody comes home, they can't flip it on you when you're up there working on it and zap you. So, industrial lockout tagout procedure. Even if you don't use the whole procedure, I just wanted to show you kind of what we do in a professional environment to keep shocks and electrocution from happening. That way you can take what you need from it and apply it to what you're doing. All right, tip number 19, our last tip. Take your time. This last tip kind of segues into how I wanted to wrap up this video. I told you earlier I'd talk a little bit about my own oops moments, and you guys can tease me, laugh at me, make fun of me, whatever. But the whole point is to hopefully make you guys vigilant, and maybe you won't make the same mistakes that I did. But this first incident, my first time I ever got shocked, other than when I was a toddler and I stuck a paper clip in the wall outlet. Because who hasn't done that, honestly? I'm sure actually a lot of people haven't done that, but I did. I liked electricity at a young age. I was all about it. So my first incident, so it happened when I was in college in my lab class. My lab class had this silly thing where they do timed quizzes, and some of the quizzes happen to use higher voltages. Well, we were working on a quiz one day, and I was running out of time. I had like 30 seconds left to figure out what was wrong with the circuit, and it was running 60 volts DC. It's enough voltage to put some current through your fingers, and I found that out. I went to move a wire around and didn't realize that it was still powered on. I zapped myself pretty good. So that was my first incident. I'm not a fan, guys. I'm not a fan of doing time quizzes because, as if quizzes weren't bad enough, you have to put a time limit on it where you get shocked. That's not cool, guys. Somebody write an angry email or something. All right, the second instance was a little more recent and potentially a lot more dangerous. I had to take over a job from the previous shift. They had a bad pump that they had to change out on one of our paint lines at work, and they had changed out the pump motor combo unit and did all the plumbing and stuff, but I had to go down and wire it up after they left for the day. So I went down there, and as I was wiring it up, I was pulling the wires through the conduit, and I made contact on my hand between the case of the pump and the conduit. And I got shocked, and I was like, what the heck? Because there weren't even any wires hooked up to it yet. There was nothing but plumbing hooked up to this thing, so I was like, I shouldn't have gotten shocked. So I went and took my meter and I measured it, and I found 700 volts DC between the case of the pump and the conduit. That's a lot, guys. Under normal circumstances, that could have seriously messed me up. I might not have a hand anymore. 700 volts DC is a lot. But anyway, I was super confused. I had no idea why there was 700 volts DC on a pump that wasn't even wired up. Well, as it turns out, this pump is an analyte pump. So on the paint lines, they dip the parts into a bath where they run electric charge through the pool before they go to paint it. Basically, it helps get all the dirt and particles and stuff off of it. But they have probes in there that put a 700 volt charge on it. Well, the guys before me had already run all the plumbing and stuff and opened all the valves, so that same fluid they were running 700 volts through was going all the way up to the pump. And I touched it. And normally there's a ground wire attached to this pump. So remember, it's a recurring theme, path of least resistance, guys. If that ground wire had been on there, I wouldn't have gotten shocked because there would have been a separate path that could have taken. Now, granted, for some of you guys that do know a little bit about electronics, the reason that didn't shock me worse than it did was because I was in parallel with the circuit I made with my fingers. I was in parallel with the electrolyte solution that they were applying the voltage to, so I didn't get shocked that bad, but it tingled, guys. It tingled a little bit. I wouldn't do it again. I wouldn't recommend it. Anyway, I resolved it. I went back and I put some permanent grounds on all of the analyte pumps in the building just so that would never happen again. And the moral of this story, guys, is be vigilant, know your equipment, know what you're working on. If I had taken some time, I mean, that's a mistake anybody could have made, but if I had taken the time to look over the equipment, really think about what I was about to work on, then that probably wouldn't have happened if I had been a little bit more vigilant and taken the time to know my equipment. Alright guys, we made it. We made it through our first video. We've officially had the talk about electrical safety. We've talked about voltage, current, resistance. We've talked a little bit about how current causes electric shock. We've talked about the paths that current can take through your body and the damage that it can do. And I gave you some tips so that hopefully we can keep that from happening to you. So on that note, I also wanted to finish this video by asking, have you ever been shocked? If you've had an experience where you've gotten shocked by something, leave a comment below. I promise I won't make fun of you. But, you know, it's all about vigilance, guys. It's about, you know, sharing stories so that we can learn from each other and avoid getting shocked and hurting ourselves. So if you like this video, stick around, like, subscribe, comment. I'll see you in the next video. This is Life Meet Lightning, here to bring a little lightning into your life.